Okay, everyone. Everyone, can we ask you to all sit down, please? Also the last people. They're still here. Yeah, I think you will be divided a little bit. You can sit there, and there's also some. You can take one chair and put it on the next door if you want to sit down. Okay, first check. I'm Thomas, the topic responsible. We have here Aneta, we have the jury in front. First of all, we'll just check if everybody is here. The team of Turkey, are you here? Spain? Portugal? Romania? Central? Poland? Albania? Benelux? Balkan? Baltic? Ukraine? Italy? Greece? And Norway. Now I would like to give the word to my colleague who will do the introduction.
Nice to see you all again. I hope you had an interesting day. I also hope that you learned something new about different areas and also had a little bit of fun. Let me introduce the jury first. So, Vice Rector of Research, Dal Slipna. Doctor of Technical Science, Heat, Gas and Water Systems, Anatolis Borodinets. And Economics, Political Science, Education Lecturer at RTU, Norman Spalapka. And the last member of the jury, I'm happy to welcome Egil Zelzitis from Building Faculty of RTU. Before you entered, I hope you noticed the number of the order, how you're going to go, just so you know when to prepare. And the first team who will present will be team from Turkey, so please come here. The controls are always yours for the team who will be presenting, so please start the presentation.
Hello.
Just before we start, one last thing. We have 5 minutes to present, and afterwards the jury can ask 3 minutes questions. We will cut you off exactly at 5 minutes after your first word. Okay?
Do we have some timing to show when we are 1 minute to go.
Yeah. We will show it with our fingers. So
Okay.
every minute we will show. No. that's something else.
Hello everyone. We are Dream Team from Turkey Yıldız Technical University. My name is Erhan and my friends Burak, Merve, and Fethi. Today, what we are going to talk, we'll talk that first we intro and then we'll talk about what we need and then energy situation in Latvia and after that, according to that, our solution package for that situation and Merve tell about the sponsorships and partnerships that when there we can reach, and there will be a summary. So, but first point will be just our future. As you know, we are now living in a polluted world, but we can change it and we can live in a better way.
We made some research about Latvian electricity, and we have found out that over 30% of electricity used in Latvia is imported. And as you can see, the population is decreasing from 2009 to 2012, but the imported electricity percentage is not decreasing, instead of it's increasing. So that we thought we need electricity, we need heat energy, and recycle, care environment, and to produce our energy as a nation. So we convert energy waste to eco-friendly, factory-friendly, government-friendly, and environmentally friendly solution. So next slide will be.
And on that occasion, we found out that there are that gases goes out of the chimneys, and in our package, we are going to turn that gases into industrial gases, which are we are using and for medical oxygen and nitrous oxygen for medical, for the first three of them for medical things, and for the third one, quick freezing in food sector, fire extinguisher, and so on, and hydrogen for production of glass, and so on, as you can see from the slide.
As you see, my friends told you, we care our children, we need to do our best for them. And there's a problem that population is decreasing, so we need to, we want that population back, but also we need to produce our own electricity totally by our own. And if we waste a lot of energy, we can't. And we need heat energy and electricity because it's a cold country, and also we are importing electricity, so we have to put it stop. So this is our cycle we talked about putting on the chimney and also the places nearby. There will be two cycles. This is one cycle. It's going to be work with special gas, for example, the refrigerated gas that can work in turbine easily. We are going to use the heat of the this draft via heat exchanger, a kind of evaporator, to evaporate the special gas here, and then we are going to work the turbine with it, and the electricity that we are going to gain is going to be used at the factory, and the overproduced electricity that can be go to the national network, that's the 130 house close to that area, and then by this heat exchanger, using the cold water with a pump, we can cool the spatial gas, and with the heated water, we can use it in the factory without summer as the internal heating water system. And then there is a central hot water grid under the 130 houses, so we can put that hot water into that system. So any heat problem is also can be solved. So, and also with the industrial draft selling, after this draft is going to be sold to other parts also, as my friend said.
So we have thought about it, and according to the European Union laws and supports that kind of projects, and Latman is one of the things company here, and also I don't know how to pronounce it. I cannot say it. I'm sorry for that. And air liquid, which produce drops the gas. Okay.
Okay, thank you for listening. This is overall.
Please feel free to ask questions.
What is the benefit of your idea?
Can I answer, or you are asking to her? All right. There are several benefits, as you see, as here. One of them, there's a benefit for factory as electricity. One of them is benefit for factory as heat, and one of them is benefit for the national part of the city. I mean, the 130 houses, and also there is a benefit for hot water that for that 130 houses, and also other benefit. We are selling these industrial tracks to other areas, so we are not losing them, and we are not throwing them to the environment. So it's an environmentally benefit, and I guess that's all. That's our main benefits.
Yeah. You can ask 2 more questions.
Okay. Well, first of all, thanks for very overall presentation. You know, you touched upon the Latvian economical situation as well, which is important. But I have more question, technical question. You know, you are talking about now gaining the electricity through this system. The question is, you are producing the heat here in the chimney, and then from that you will generate electricity, which is a higher quality energy. So what is the really efficiency of the system in terms of producing electricity?
Actually, we used like freon gases, like the refrigerant gases here. So they are evaporated in the low Celsius. So and also the point at here is 180 and between 240 centigrade Celsius. So we can make the turbine work, but it's also about how the turbine is going to be made. And especially without a lot of technical information, we couldn't calculate the direct efficiency. But we believe that we can create electricity, we can generate electricity. Not a lot of true big amounts, but especially we can use it in this way.
My question is, well, why electricity? Because they maybe go directly to the heat exchanger. So using electricity would be more efficient and more economically beneficial. That's what my question.
Then we didn't want to use any part of it. We want to use in each area.
Are you asking for why did we choose turn into electricity?
Yeah.
The thing behind it, we are in an eco-friendly world, and European Union supports us so much, so we need the economical support at some point. So electricity works out well, because in the case it was true that there are 20 cars according to 130 homes, so it's 15%, and it's too much for a city for now. So it may raise, that's the reason why we did it, and also we are going to sell it to the national government and so on, and we are going to have some efficiency inside of the factory by using the electricity. That's the reason why we have used we did turn into electricity.
We also wanted to support the Latvian economy because Latvia imports so much electricity from other countries.
Okay, thank you. Thank you, Julie, for the questions.
I guess we have one more question.
The time is over unless you can make it in 30 seconds. Maybe really quick.
Difference in Latvia, you said that 30% Latvia is buying from some work, but did you recognize some difference between winter situation and summer situation? Is it for And we have total or
It's all these are the year total values.
total
Yeah.
conditions for all over the year. Yeah?
Started by the working on all over the year. So,
Okay.
They're all
Okay.
yearly knowledge, so we
I
just
got your answer.
thank you
Alright,
very
thank you.
much.
Thank you a lot.
The next one up will be Spain and Portugal will get themselves ready.
you know what?
Good afternoon to everybody. I'm going to introduce my team. Is David, is Pablo, and is Raquel. I'm India. First, we are going to introduce the students, the introduction to our idea, which is the problem, which is the solution, and why have we chosen this solution. At first, as we have read in the handout, the technology is not all in the industry. It's just the solution and the development we do to this project. So yes, we have seen that power plants have a very energy waste, so we have to manage this, and we think we have a very good solution to this problem. As we can see in the industry, we have the technology is based on the nature, and we have based our idea in this. Our inspiration is from the industry. We have seen about pets are her cycle of good pets. In the nature, they should would be atomic, but in the industry, they use for X-ray by the technology that they have used is use beauty with light this term of this term on. So my partner is going to explain this.
The principal problem in the industry is that we need energy, but this energy produces power and work, and another type of energy who is lost like heat. And this heat, we have two ways for working this. We have for to change the process, we must to minimize the heat loss and use the necessary heat. Sorry. To minimize the heat, we have to put in the same temperature the atmosphere in the fabric and the atmosphere near to the fabric. Because if you have two parts in the same temperature, you cannot heat. And could we use this quality heat? We are going to work in the refrigeration tower we have over here the steam. But we are going to work in this area. It's a wet liquid, and the process is that in this area the plants can take easily the water with the roots. The solution is
I want to tell we have chosen as the main branch of the energy of our factory the combustion energy, which is to heat steel and for the rolling machine.
So what we have to do is to use this efficient, but rigorous in its language. So our target is to use that. Our purpose is to use robots, and we will pick up at the domain zone where there is a device similar to a water treatment plant. This is the device used to accelerate the delineation process of the plant. So there will be a machine who will proceed then the delineation process with the sound and the light. Because here is going to be the speed of the plant. Who simulates the evolution of the sounds. And then when the delineation is ended, we have the continuity plant and the one.
So the flows here is the people from the city give rubbish to our compost plant, which is located behind the factory, and later we use this compost to plant new trees in the forest and to plant our own plant. This solution is so friendly.
George, any questions?
I think it's an interesting solution, but the question is always, who will be the users of this compost or residues you produce in the process? Because they should compete with the local fertilizer company. So how do you convince them to buy your product instead?
On one hand, we're going to use our compost to plant our own trees. And we are going to germinate the trees in an accelerated process with the machine we have detailed before.
The natural process in the germination is 10 days, for example. And in this process, you go quickly because you have the same temperature in 5 hours, like in a day. And if you repeat this operation quickly, you can have, and in the next when you have a very big quantities of plants.
So the plant is situated in the middle of the city, so how the outdoors will affect this quality? I mean, how the outdoors from these processes, the smell?
The smell. Well, is it isolated? Or the process is
So the process is insulated from
from the environment.
You need the extra land for this process? Extra land.
You say you have
Extra space or
yes.
Yeah, for the extra space, we will have to build the structure of the device to turn on the ground in order that they complete the delineation process.
Over the factories.
Yes.
So you need an storage for the compost. We can make a batch here. And this is the complex.
Thank you. Thank you, Ms. Spain. You're welcome to present, and Romania and Moldova can get ready.
Good afternoon, everyone. I'm going to present to you the work that our team did in case study 1. We are a team from Aveiro in Portugal. I'm going to present to you what the challenge was. Then we're going to put in some numbers of the problem in order to have a better idea what it's about. After that, we're going to present our solution, and in the end, I'm going to show you the pros and cons that we found for the solution. First, the problem. The problem is very simple. We have a factory and nearby we have a certain population with 130 households and public services. The question is, the fabric is wasting heat from the smoke that it expels from the chimney. And we want to use that heat somehow. How can we use it? Let's see. First, let's put some numbers, like I said. This image is simply for scaling to compare the size of the chimney with the size of something that everybody knows, the Eiffel Tower. We looked on the internet for chimneys that had approximately the same height that they gave us, and we found this. This chimney has a base diameter of 23 meters and a top diameter of 18 meters. Next, we looked for enterprises that smelt steel on the internet to see what kind of gases we could find in the smoke of the chimney. And we found these approximate percentages. Additionally, the gases go out at a rate of 1,650 meters per second at the temperature given by BEST, which was 200 degrees Celsius. Using this small equation here, we can calculate the power that the plant has stored inside the chimney as thermal energy in the smoke. We have to perform that multiplication, considering a difference of temperature of 4 degrees Celsius, we achieve this power. This is, of course, ignoring any losses in transport and production, as we will see later. Also, now let's look at the town, because it's the enterprise one. Let's look at the town. The town has 130 houses. We searched for on the internet what was the average energy spent per year for each household. We also found that we have an average of 2 people per house in Latvia. And using those calculations, using certain values that we found out that the total power required by the small town around the factory is around 79 kilowatts.
So what's our solution? It is simple. We will grab the energy that is stored in the chimney, and we will have 2 heat exchangers. One that will provide energy for Stirling engines, and another one that will provide energy for a closed water heated circuit that is already installed in town to perform the heating, house heating, and the water heating of the town. Water heating, like the one we use on that, and house heating for the environment. We calculated this exchange efficiencies by considering the toroidal set of toroidal heat exchangers in copper with these specifications, and calculating these calculating the total area of the system and the heat function, we could achieve a 10% efficiency for each one of the coils, assuming a 4 degrees Celsius drop, 2 in each coil. We are assuming that drop, and we haven't done the calculations about if that drop can be achieved. It will depend on the flux, and we didn't calculate it within that time. And what we got in our solution, well, our solution we can see by the numbers. We have a giant producing energy for a little. Even with all the efficiency issues, we will have an excess of 19 kilowatts of energy produced this way, so we could provide energy for the town and we can sell it for the city.
So let's take a brief look at the cons. In this way, we have a single source for both electricity and hot water for the town and for the outside if needed. The hot water supply is already connected to an already existing central water grid, as was reported to us. The investment from the company would be around 150,000 euros just for the Stirling energies, but the return on investment would be in about, that is rounded, so 4 days is 4 trimesters, a bit more than a year actually, without counting the pipes installation. The maintenance of Stirling engines is very cheap. It's about 0.6 cents per kilowatt hour provided. The eco-friendliness is achieved because we are using energy the heat energy from the chimneys that would otherwise be wasted. As cons, we found 3 main cons. If the town was a bit larger or the company a bit smaller, we would need a different system. And time is up. Thank you for your attention.
No, thank you. Nice presentation. On calculation, it looks like it will be somewhere as a comma. I think 79 kilowatt is, I think it's usually its average capacity of small apartment building. In your calculations, it's all consumption for city.
Before years, yes, but we grab the data from the average household consumption, the per capita, it's not per household, it's per capita, right?
No, it's consumption was per household.
Household, okay. The household consumption of a Latvian household, and we say that it was
3,500 kilowatts in a year.
That's good.
no kilowatt
It
power
said per household.
per household.
Because we were told that we had 130 houses, so that's what we're working on. Not
We also found that the numbers were small, but we checked the calculation once again.
Yeah, it's just I want with 39, it's usually relative for kilowatts of single family houses. Single family house is something like 15 kilowatts here. And here the whole city is 17.
But this is all the time. It's, you are talking the installed power, right?
Mm-hmm.
There's some difference between installed power and really active power consumption. Because if I'm not using
So it's the kilowatt hour.
this is an average. So I'm not always using the toaster, I'm not always using the heater, I'm not always using everything. This is the average consumption over the year.
One chimney can produce energy
for a whole town, we 130 houses.
Yes, that's a real small town, that's what we are showing in this picture.
Also, we were as surprised as you are, of course.
You produce constant energy, right? The consumption is changing all the time. How do you compensate that? And during this winter and summer.
But the energy is injected in the grid, like.
Okay, so the grid would be to compensate.
Yes, of course.
Also about the energy being constantly produced, that's actually true because we were told that the factory is to be assumed to be working 24/7.
Okay. Thank you very much. The next one, please, Romania, Moldova, and Central Thinking Trading.
Good evening, ladies and gentlemen. We are the case study team from Romania. We're going to jump really fast into it because we have a lot to show you and not enough time. I am Matei, this is Radu, my colleagues here are Irina and Ioana. So first, we thought about how are we going to harvest the energy, what will we use it for, and then we thought about a solution. We're going to use it for heating, electricity, sodium dioxide harvesting, gypsum harvesting through air scrubbing, you'll see that in a moment, for hot water for the town people, and for the organic Rankine cycle, we're using the waste heat to produce electricity. We thought about an intelligent and efficient use of using the inherent high heat of the plant, seeing as we're working with a steel mill, and as you all know, working with steel requires a lot of heat. And then we thought about how to transport the heat, and then we thought about the simplest way to conduct heat through tubes. So first of all, for the chimney itself, we are thinking about using air scrubbers, first to desulfurize the flue gas, so we can clean the gas and harvest sulfur and sodium dioxide. And then we found out that as a byproduct, such a scrubber would produce gypsum in modest quantities, but it could be used either for selling or for construction purposes. Next. As an example, we looked at the sodium dioxide emissions of America, who uses the most, who utilizes these scrubbers the most, and we saw that in 29 years, their sodium dioxide emissions have dropped considerably. Next, we thought about using the heat to, actually, first of all, we thought that we could use a steam turbine combined with the heat from the plant so that we can produce electricity during the summer and when it will be good as far as weather goes. Then we thought that we could go a step further and renounce the central heating grid of the town and move it towards near the factory, so we can produce a hot water grid from there and transport the hot water towards the town. Then we thought about how we're going to transport the water through the ground in Latvia, a cold country. And then we thought about using aerogel as an insulator, which is the best insulator known to man. Intrinsically cheap, with a high return value because it does not decay. It's basically another way of arranging carbon or silicon. Next, we have the ore, which is a heat processing unit developed by Siemens, which uses waste heat and transforms it into electricity. It has, as we've seen, a low operating cost. It's very low maintenance. You do not need people to operate it, so it's unattended operation is possible. And then we thought about the winter conditions where we could not use the steam turbine to produce electricity. So we thought about thermoelectric plates. So basically, we haven't used the chimney up until now to produce electricity. So we thought about using that. We saw that we had almost all year round a delta temperature of 100 degrees or more. And so we thought that it would be a great medium to use thermoelectric plates to produce electricity within the chimney. So the communal impact of this system is that heat can almost be entirely produced at the factory and given towards the town people. The town would pay lower prices for heating. New workplaces will be available for all of these systems to work. And the town's electric bill will drop drastically due to the amount of electricity we will produce through our systems. The industrial impact will be that the chemical and the construction sector will have a help as far as sodium dioxide goes and gypsum goes. It's almost cost-free. It's just you reusing the waste of the plant towards another purpose. And also, again, new workplaces will become available, which will help the Latvian economy. Then we thought about possible sponsors. We already said that Siemens develops the ORG technology, which they could be interested in sponsoring. Procter & Gamble also is a big fan of energy efficiency, Emerson as well, and also Red, a recycling company. So the conclusions, economical growth to local sustainable production of electricity and heat will be possible. People have reasons to stay in Latvia because of new workplaces and economic growth, and that's all.
Perfect timing. I mean, you have posed many advanced technologies.
Not that advanced. All of
But
them
anyway,
are used.
I mean, quite complex solution with many steps and so on. The question is very simple. Who is going to be invested in this project?
We've seen from all the technologies that they are not produced. They are produced only in bulk. So it could be an industrial project, an European project, European funds, and the prices can be negotiated. Most of them have a high return value. So
you suggest structural funds to be used for this?
Yeah, exactly. And also all of the other firms that could be interested in such a thing, like Siemens, Procter & Gamble, Emerson.
I mean, they will not go for one plant.
Not just one plant, we want to generalize.
Okay, thanks.
Costs, is it for
approximately?
Yeah, approximately for city scale or capacity, what it costs?
For a very large factory, so we can cover everything, so we can have an even higher return value cost. Because the plates would have to be put near the furnaces where the metal will be melted, so we can have a higher electrical output, and we'd have to cover almost the entire building in a grid intelligent system of tubing, so we can give back to the town heat and electricity. Thank you.
Okay, before we continue, you feel it's a little bit getting hot in here. We could use a factory already over here, I think. So we will have 2 minutes break that we can open, 5 minutes break that they can open it, go to the toilets or whatever, and it will be already cooler when you come back. So try to keep it short.
C'est ce que je pense que effectivement, si vous connaissez, para está tudo bem, tudo claro, está tudo bem, não é que não está tudo para assim. A questão é aqui com o seu curso, eu não para
Sabe que não era mega outro, mas yapamıyorsun, yapmamam.
Are all the teams back? Are all the teams back? Refreshed, ready to continue? Not so hot anymore, thankfully. Okay, sorry, guys. Can you hear your team their jury? Awesome. Okay, if everybody's good, let's continue. So next up is going to be Central and Poland. Get yourselves prepared.
Hello guys, I'm Jadis. I would like to show us our project. We named it Recycle. We are from Central, we are from Slovakia University of Technology. So we thought, what were we supposed to do? We had a factory there, and we wanted to use some of these heat to actually make something better of it. So we thought out a way to save resources, help nature, and save some money also. We want to do it by heating water, which we can do in the chimney. So we connect the industry and the homes to the hot water supply, so they can produce something or use it as they want. We wanted to focus on heating-based industries, so we could provide a waterfront for them. So we thought of like recycling and paper industries should be good ones, because they need to heat actually some processes, so they can use the heat to melt paper or metal plastics. And it's also the path that we can use it on any scale. So if you have a small factory, you can actually use the heat only for heating the homes, but if you have a large factory, you can use it to provide power for the industry, like mentioned before. Yes, the technology behind it is actually basic. We don't want to do anything new, so we use just basic heat exchangers. The fuel which comes out of the chimney will be used to heat water to about 200 degrees. So the bigger the exchange area is, the more power you get from the chimney. Yeah, we also wanted to do not lose any energy in the process, so we are not making electricity out of it. We're just using the heat from the water. Also, the distribution is basic. We only need pumps and pipes, which can be then used for the central heating or the distribution in the factory, which should be nearby. And that's the stuff we actually like to focus on. So the industry should be near the factory, so it's actually more efficient if you have built the factories near the actual steel mill, so it can provide also some jobs, but also really efficient. Yeah, so this is the integration that looks like this is actually not the scale, just to show it. So we wanted to have a large exchange area, so we can provide as much power, to give as much power to the system as we can. So as I mentioned before, the output is hot water, and we don't actually lose any power in the process or any energy in the process. So also the use of latent material is advised, so the losses are even small. So let's take a look at the one steel mill we mentioned before. So we thought the actual usage could be around 50% of the heat should be used. So some heat has to stay in the factory, because then the chimney actually won't be efficient at all. Yeah, so we'll use the 50% of that power, and it should be enough to power a small factory, recycling factory, and enough power to supply the village with hot water too. Yes, so we mentioned before, we want to recycle stuff with this technology. So in this case, we'll actually like to recycle the plastics because the water should be hot enough to melt the plastics. And then actually the recycling factory won't have to use any power to heat the stuff. It will just melt by the water, and that way we will save more money. Yes, technology is still it's quite easy. Just heat exchanger and with the pipes out of it, and then put it directly in the factory to melt stuff. Also, we would like to provide a hot water village, so people can use it anytime they want. They can heat it in the winter and use it for AC using the heat pumps. Yeah, also we mentioned we figured out that the steel mill produces some excess electricity in the process, so that could be used to provide the electricity for the village too. Yeah, we thought it should be actually pretty sustainable because we have to recycle, and it should also help because the industry could get some invitations from the country, so they will have enough money for the recycling. It's not feasible. We are not doing anything crazy. We just like to use technology which is current. It should be easy to do. We don't have to worry about much going wrong, and it's also not really expensive, as you can see, and you can use it in any area you want. And stay with it.
Very prudent solution. I think it's nice. The question is again, what are you going to do in summer?
In summer, you can actually still power the factory for recycling. So you can still mold the stuff, and in summer you can use the hot water to produce cold air with the heat pumps. So you can actually do some air conditioning with it.
Yeah, that is not common now to have this deposit system for the plastic bottles. So they're not spreading them in separate boxes. So when you are able to take these plastic bottles for recycling?
In naturally, actually, this was just example from the steel mill. But you can actually recycle anything like paper or anything which melts at that temperature.
Yes, you should have some special system for the waste.
Would you say some place of Latvia or some city in Latvia is very open to
We actually didn't research that, but I will tell you in general.
Great, thank you. Thank you to the central. So the next one up is Poland. Please come, and now Padre can get ready.
Dear jury, dear guests, organizers, dear participants, my name is Marek, and together with my friends Łukasz, Paweł, and Jarek, we represent Poland in this wonderful competition. And right now, I'd like to introduce you to our solution to how to retrieve and recycle heat from factories. During this short presentation, I'll describe briefly EBEC effect. Then I'll describe a bit more extensively our solution. Then I'll move to benefits and beneficiaries, as well as sponsors, and finally I'll quickly summarize my presentation. Any questions? Shall we move on? EBEC effect is a simple thermoelectric phenomena discovered by Estonian physicist, and basically it's conversion of temperature difference on the junction of two conductors or semiconductors directly into electricity. there's another phenomenon that works vice versa. Here are the junctions, the temperature difference. It's basically multiplying temperature difference times the coefficient difference. That's the coefficients are explicitly stated for all the elements that you can find in the world. Before I move to our solution, I'll try to explain how the chimney is built. First of all, what we see from the outside is just a shell, just a cover of 3 separate canals that are inside. That's where the fumes are. And it's separated into sections by the surface levels. We decided to install our the junctions for EBEC effect on the surface levels first to provide easy and quick construction, and second for the maintenance costs. Inside the chimney, where the temperature is the highest, we'll have one junction and the other one right in the center of the whole chimney, so we can get as high temperature difference as we can. This is a brief estimation of the benefits we can get. It's based on what we can find on Polish plants. One Polish steel mill uses approximately 130 megawatts. 50% is waste. EBEC effect is just under research in Poland. The researchers have successfully regained 0.5% of all the waste energy, but they're really optimistic about the future. So in our estimation, we decided to adopt 1.5% efficiency factor, and that's more or less equal to 4,000 electrical energy powered cars that drives 10,000 kilometers per year. Moving to budget, it will be approximately 7 million, but research, which is the biggest factor in the budget, has to be done only once to develop and discover which junction, which elements are the best for the needs we have. So if it's split between more facilities, it will be, of course, cheaper for each and every of them. And savings, energy produced will be approximately worth 1 million euros, but it's a save, not a profit. Because we decided that this free energy will be given for free under some conditions I'll state later. The benefits, local authorities, society, factories, electrical car producers, and environment. Since, as I said, we decided to give energy for free for lights in streets, public facilities, and electrical car charging. That's where we want to search for sponsors. Electrical car manufacturers. As well, European Union, it's green energy, so it's on top. It might be an ally on the CO2 emission war we are actually on. To summarize, we delivered a solution that is both easy, can be easy constructed, and in multiple situations, in cars, in factories, in power plants, etc. Thank you for your attention. Are there any questions?
Well, it seems so simple. The question is, why not being used now?
As I said, this solution is under research right now. It's 0.5% efficiency might be a bit too low right now to introduce this solution at the moment. But as the time passes, the researchers will come up with better solutions, with better elements, with better junctions, etc. And when the solution will be better, it might be introduced in 10 years, let's say.
And the new technology to be introduced, it will take more than 10 years.
It's just a quick assumption.
Thank you. you're up next, that's nice. And the next country, you're going to be after them. So in a country, the theme.
Let's just do it in random order.
Okay, hello from my side, I'm Bettina. These are my team colleagues, Philip, Katja, and Marcus. We are the team from Alpiader from Austria, and we're going to walk you through our solution for the heat recycling detectors.
Okay, as you saw in the handout, the current situation had a few assumptions, and one of the we took two additional assumptions from this. One assumption was that the existing central hot water grid was already powered by this steel mill, because it's the only logical way how you would power a municipal hot water grid, right? So probably there's already a cogeneration heat engine in this steel mill already there, because also the flue gases are already cooled down to about 200 degrees centigrade. Well, steel does not melt at that point. And also probably, since this takes some time to deploy, it was, well, very likely installed already a few years prior to that. The other assumption that we took, because we're not chemists, we assumed that the main flue gases, and we looked through a few articles from steel mills, are most likely carbon monoxide and carbon dioxide. Okay, the solution that we propose is a two-part solution. The first part is to modernize the cogeneration system that is apparently already in use. Here you can see a modern version done by Siemens. Cogeneration systems, older ones either put out heat or electricity. Modern ones can put out both. This cogeneration system would have the effect of reducing the gas temperature even further down, so below 180 degrees centigrade. With these cooler exhaust gases, we then use a quite new technology, which is already on the market, which is called gas fermentation. Gas fermentation is something that is used to produce biofuels or chemicals in general, and this is done to reduce overall emissions, especially of carbon monoxide and dioxide. Gas fermentation works like this. We found already 3 marketable solutions, so solutions that are not just in the testing phase, but that are already deployed around the world, for example in China. Lanzatec works with archaea. These are very ancient bacteria, kind of. Phytolutions works with algae. You can see here an algae farm from them. And Bioreca works with a combined approach. These systems have a projected lifespan of about 25 to 40 years, and a quite low or high, depending on how you look at it, return on investment of about 3 to 10 years. This return on investment is quite low or high because the products that this technology produces are quite looked up.
So of course it would require company investment in the beginning, but through the sale of the additional products, of course, the return on investment can be minimized. Of course, there are CO2 certificates, which you don't need anymore because you feed the CO2 into the microorganisms. And there are European funds, for example, the Horizon 2020 or the SILT, the Sustainable Industry Low Carbon, which applies to our technology here. So the overall benefits of this combined solution is an emission reduction, because you use the gases to feed the bacteria. There's no impact on the hot local water grid, because you continue using the system that is already in place. Excess heat generates electricity for the town nearby, for the electric cars, etc. One big point, biofuels, the fuels from a renewable source, which if this is used not just for this very company, but maybe Latvia or the whole Baltic region, the region can take a pioneer position, maybe even in Europe, because it makes it more independent from imports. So in general, fewer resources are wasted because you convert the waste to resource. The overall conclusion the marketable solutions are there. The main challenge is just to find the right ones for your company or your environment. And this thing or mode of thinking for the future, waste can become a new resource and should be treated as such. Thank you for your attention, and we're looking forward to your questions.
Very small period of recruitment investment. Did you have any calculation?
We looked through it. It was that we get these funds from the European Union. Without it, of course, the period stretches.
Technical question about the using measures. So I saw the pictures. You're going to put it in the greenhouse.
Yeah, in this case,
So you cannot do it in the mixed tank.
yes, you can. There are different ways. In this one, you have it covered. According to them, they can work until minus 30 degrees or something like that, and up to 40, and use the heat of the waste here to warm the whole thing up. So keep it warm and also need time.
But these are for the profit, but you still need light, right?
Yes, so you would need to have at least somehow the snow from the.
So probably is not the solution that answer take is more appropriate.
So
it's something that depends on a lot of sunlight.
Yeah, like the sorry, they don't need any slides. They use other means of reproduction and consumption of the microfilms, depending on the microfilm.
They are harvesting from these deep sea volcanoes.
Okay.
So another question: what you produce the biomass and the biomass complete?
Then you fermentize it usually, or
into what?
In ethanol, for example, to produce biofood. There are other components that where you can produce other chemicals, especially for the bacteria one. They are researching for other kinds of bacteria. You can produce other stuff. Also, you can use it for as biomass to bring into biomass plants, or to use it for feeding for animals.
Thank you very much. Please, Team Benelux, come and present your work. And Team Balkan can prepare themselves to come up next.
Simplicity is the ultimate sophistication. So, good afternoon and welcome. My name is Nicolas, and I will be presenting on behalf of the Visionary from Benelux. The problem statement that we derived is as follows. Industries often do not have a system for capturing, distributing, and reusing waste heat from factories. That's the problem we were focusing on. Our solution had 3 different requirements. It had to be original, realistic, and also socio-economical beneficial. Our solution. Instead of trying to transform the waste heat from factories into something else, we wanted to use the heat directly. And in that thought process, we came to using greenhouses as a solution, because they are a major consumption of heat, and they also, similar to the factory, they run continuously. As I said, we use a very simple system. We first have our heat exchanger, the first heat exchanger here, to transport the heat from the factory into a water system, a closed water system, transport the heat to transport it to the greenhouse, but it will be led into a second heat exchanger, which can warm up the soil required for the greenhouse and also regulate the temperature inside the greenhouse. And it's a closed system, so the cold water returns back. Next slide. A little bit zoomed in. Of course, our transport will be done through insulated PVC pipes, and this is a zoom in of the heat exchanger, but I will continue with that. In conclusion, we have a simple solution that can be widely applicable in many different cases and can be adapted. Investment costs, we estimated for a small to medium size commercial greenhouse, and we estimated the total cost to be around 162,000 euros. And you can see the cost over there. Next slide. The operational cost, we expect the operational cost to be around 60,000, expected profits around 100,000, expected lifespan of 25 years. And this results in return on investment like this, because we started with gaining profits from later on after we already constructed the building. And after 7 years, we expect it to be profitable. Social benefits. Why we use this solution for job creation. Latvia has a lot of unemployment, and this can create jobs in the greenhouses. The second thing is we have less. You have to get less import, and that means cheaper vegetables for all consumers in Latvia. Less import means less as a byproduct of the less import. We also have decreased CO2 emissions because of less, decreased transport, and of course we reuse waste energy. We also have economic benefits for the factory. They can gain a sustainable image. We have low investment costs, so it doesn't have to be a big project. We don't have to have humongous investors trying to invest in this solution. We can do it with a relatively low cost. Decreased dependence on import, and we also see that we can promote local investments, governmental investments, and get the economy running. We do have a few limitations to this, and that is that in summer, the solution may not be as effective as in winter, because there might be a surplus. That's something that is just one of the limitations. And it may not be as applicable in larger industrial areas, but it will suit the smaller local industries that are booming in Latvia. This was our presentation. Thank you very much.
So what would be alternative solution instead of greenhouses? For example, we're focused on greenhouses, there are a lot of limitations, but what would be alternative?
For using heat?
Yeah, to utilize heat.
Well, we've considered trying to transport it also into the main grid for heating houses and water, for example.
Yeah, because we can use not only greenhouses, fish farms, for example, some recreation farms also.
Yes, of course, but the main advantage of greenhouses is that we can provide it in the area of the factory, and that we don't have to have long distribution lines. So we would also have waste loss and additional cost, and we are not sure if the amount of heat that is residual is sufficient to also provide energy to other areas.
And also to add is that the whole reason we chose the greenhouse is because it burns continuously. And
also around.
It's a recreational,
Yes, well,
for example,
that
in the
could
main
also
house.
be.
Yeah.
Okay, so why not applicable to industrial parks?
Well, you would have to increase the size of it as well, and yeah, okay, it may also be applicable actually, but it would add extra difficulties. So it would not be an as simple solution as we described here, but we would have to adapt it.
I think the only reason for that is also that
so much space.
Yes, for example.
Yes, and also the chimneys in the center, you may have to pipelines and
And you thought about the business model, how to run it, because it involves a chain of different businesses, including, planting and so on and so on. So who is going to own it and who is going to run it?
Private, I think, yeah, it should be privately owned, and farmers from around could perhaps also.
So you kind of rent out the space, and you move rent out the space for the farmers.
Yeah, due to the low investment cost, so it's actually accessible There's a lot of people type.
Okay, thank you very much. Please come and robotic team prepare themselves.
Dear jury, dear competitors, let me introduce my team. Firstly, this is Nicola, Sasha, Philip, and me, Christina. The main goal of our project was thermal energy, and there are a few reasons about that. Firstly, because it is environmentally friendly. Secondly, because it is a single investment. You pay once and you use the benefits in longer terms. And because of the, we covered multiple buildings, not only the houses in that area, but there is police offices, schools, etc.
Hello everyone. Like Christina said, we are planning on focusing on thermal energy or heat energy. According to the test, we have a small town of approximately 130 households. The water consumption based on our researches in Latvia is about 100 liters per day. Our solution plans to cover about 50% of the total hot water consumption in the entire year. For the solution, we are planning on building a system based on pipes that will be installed inside the chimney. We plan on using pipes called EIN 2448. The pipe size will be 100 millimeters. Total pipe size length will be approximately 500 meters because the chimney in the past was about 175 meters. And according to our research, we will need about 8,000 euros to buy those pipes. And the flux that those pipes need to provide is 270 liters per hour.
Okay, so you heard a lot of pipes and you did not hear the explanation about using the pipes. Actually, we are focusing on implementing a simple solution that will be installed simply, that is already proven, and that will heat the water and use it for heating our households, or maybe using it for our bathing or something, if applicable, of course. So let me show you the elements of the system. So we are talking about the chimney here, and these pipes are installed in the chimney. So they are like coils. You can put any size there, meaning you can do a lot of circles. You can do them like this or like this. You can do that. And the system works this way. So you have this fresh tank of water, of fresh water, and that's cold water, and you have here hot water tank. So there's a pump who pushes the water through these pipes and into the chimney, which operates of temperatures from 180 to 240 Celsius degrees. So the water heats there using the chimney's power into the chimney smoke, and then you return it to the hot water tank. Here you plug the central hot water system. Next slide, please. So we're using that system. Why are we using that system? Because there will be no additional piping system required to be installed in the area that we are covering. So the connection will be done by pipes. This is very flexible because it is easily adjustable to different requirements, meaning that if the chimney is larger, you can use more pipes, etc. And of course, to reduce the amount of power of energy decrease, you will have some insulation. For the storage tank, we will use insulation blanket that reduces the heat loss by 25 to 40%. That causes 49% energy cost savings, and the blanket price range is 75 to 150 euros per meter square. So the payback period for this is approximately 2 years. Next one, please. Okay, and for the hot water pipes, we have foam insulation. That is heavy-duty pipe insulation with over 8 inches thick walls, and it is easily insulated over existing pipes.
As our conclusion, we have our capital triangle. We have our sponsor from one side of the triangle, our factory from the other side, and the third side are the society. So it will lower the expenses. It will have 0% negative environmental impact, which is, and the result is overall happiness. And there is a smiley behind those words, so it's not invisible. You feel free to check the people when they are paying their bills. So you will see the smiley, and also the sponsors will be happy. Thank you.
About 2 years, yes. But this is the payback period for the. No, we cannot say exactly the payback period in the exact amount because we do not know the income of the factory. We do not know what's the amount of money that the factory produces, and So we did this research where a factory, which is a medium-sized factory, and with this amount of one slide back, please, we said that we will need another one. Approximately 18,000 euros. So the payback period is about these pipes. So we're not covering the pipes from the central grid system because that is already covered, of course.
So please correct me if I'm wrong. So you are going just to place the simple pipes inside this duct?
Inside the chimney.
Inside the chimney.
Yes.
So what kind of pipe are you going to use? I think it's
you can use a copper pipes because they have a temperature of melting about 300 and 1,000 Celsius. He did the research about that. 1,000 Celsius degrees, meaning. Okay, meaning this system is already implemented. You can have this one in your house boilers for heating the water in the boiler, inside the boiler, and etc.
Wait, what water for what? For is it drinking water? Or
No, it is not drinking water. No.
So heating of the.
Yes, it is for household heating. You can use it. If I understood correctly, the task it is a central hot water system, right? So it is mainly used for heating. If some of the households have these boilers with pipes in them, you can do a research on that. There exists. I have it at home. Actually, you can put this hot water system in them, and that holds the water inside the boiler. So you have showering water because the water inside the boiler is not the water you are running through the pipes. Do you understand?
Yeah, I do understand.
No, it was my English. I'm sorry. I didn't mean to.
I was just wondering if again it's a heating system, so it's how it's flexible. How flexible it's going to be. It's simple, but it's not really flexible.
Meaning?
Meaning that you have a consumption. The heat consumption is very different over the year.
Over the year. In the factory, right?
No.
The consumption for the people. We have about 130 households. I mean, that's not a large number, and we are mentioning large factory. I'm sorry?
It will be shut down during the summer.
It works 24/7, 365 days in a year. That's on the task. Yes, you do not need heating, but you can use the heat for something else. For example, in factory heating.
Okay, you didn't say that.
Yeah, I'm sorry. I'm sorry. You can do that, of course.
Okay. Yeah, good now?
Yeah. Thank you very much.
Ukraine, prepare yourselves. You're going to come after Team Baltic.
Hello everyone. Presenting my team. So we're Latvians neighbors from Lithuania, and we're 3 classmates and our other mate. So we are presenting today our solution with the chimney. So as you already know, what were the tasks? So we try to recycle the heat from the chimney. And basically, we can make 2 forms of energy, such as electricity and heat. So what we can do with them. In this game, I would like to represent our point of view how we would like to use the energy from the chimney. So we're using the pipe system from the copper inside the chimney. So we're producing heat, and the heated water going to the turbine where it's compressed and electricity is produced. After that, the heat can go to the central heating system and heat the household. Other way is to produce electricity also with a thermal generator. It was presented before. And after that, it's very flexible system because if you don't need any heat water in the summer, you can produce electricity, and in the winter you can produce heat water through the central heating system.
Here we see the section of our chimney. In the chimney, these white pipes are Cooper pipes, which are made in spiral. The blue circles are pipes which are used to cool down our thermocouple because we need a big difference from temperature to gain electricity. And that water which is used to cool down the thermocouple is going back and joins the Cooper pipes to heat water even more. So water is heated until 90 degrees. We can see it here. The cold water comes, and after they go through the chimney, through hot fumes, we get hot water.
Okay, it's another solution how to collect the energy is to use thermoelectrical technology, and how other friends from other countries mentioned before. We use this technology uses two different thermal electrical oxide materials. One is a positive, and another is a negative, and it's two surfaces between in the side of them. One is a hot one, and the other is a cold one. And the hot surface is inside the chimney, and the cold one is outside of the chimney. And the temperature difference between these materials creating electrical potentials and electricity flow.
Okay, so our calculations show that it's possible to light up about 28 kilometers of street lights. Our calculation says that it's possible to supply electricity for 80,000.
It's made a mistake with the calculation. It's actually 15 households providing electricity for all year.
Yeah, the savings is up to 275 euros a year. So the general benefits for society is more eco-friendly energy. It's also lower than energy costs and help the environment. And benefits for factory, less wasted energy, extra income. Extra income is to expand production and investments. And as I said, as my colleague said, two types of energy supply. And we just calculated that from 10 to 25% heat energy could be saved if we use heat. And we can use heat production during the winter and electricity during the summer.
This is the project's cost and turnaround. The overall cost is a bit more than 2 million euros. And the turnaround time will be from 7 to 10 years. And the lifespan of our system is really long if the maintenance is good.
So that's it.
Yeah, thank you. Very nice presentation. All very clearly described and explained. So, do you know maybe there are some real case study about this?
Yes, we know that the pipe system from the cooker we can buy. It's actually produced. Yeah. and the efficiency of the system is from 10 to 35%. It's of that system. There's not our idea. It's 10 or 35%.
And there are even companies who made chimneys with the system, and then Danish people are into research of the second solution to create the electricity with those thermal couplers. So they are investing over 18 million kroner per year.
It's basically the same thing you can do in the cars with thermal. So we can do it the same with the chimney.
And this already is achieved by using the same system the sewage collectors, because we know sewage is already has some heat inside. It's the same.
When the stage is yours, the next one up will be Italy.
Okay, so we can start. Hello to everyone. This is Team Ukraine on board. I want to present my team. This is Margaret, Vsevolod, Anatoly, and me. We are representing Kozak capital, Zaporizhzhia, and we are from Ukraine. As we know, we have a big amount of manufacturing in the whole Europe and in the world. So it is an actual problem because of economic crisis. We know that the amount of the factories cannot stop, and they need to produce new products. So we cannot decrease the amount of fumes that they produce. And as we know that the development of alternative energy sources also develops, and we have some emerging resource and inventions which force us to find the great solution, but we didn't find it. So we every day face with this problem, and we want to put a big full stop on this. So we want to present our solution. The actuality of this problem that there is a new source of energy. We want to solve the problem with heating, and all these facts should require in our solution. We also provide a new global system which can be useful for all the world, and we also collect and reuse the wasted heating. The problematic with which we are facing is half of energy is wasted during the manufacturing. The reduction of CO is very big, and the maximum reuse of we want to use the maximum reuse the maximum of wasted heating, and we want this heat to be used by the zero.
So now we want to represent our solution. So we named our system Effective Eco-Safe Energy Pipe. So this system consists of some parts. It's like conversion system of waste heating into electricity energy, decreasing number of emission, supply system of transport energy, and decrease number of CO2. And now I want some detail on this part. The first conversion system is implementation of turbine, but not one. Maybe it will be a cascade of turbines because the pressure on the first will be max and lower to the next. So here you can see this turbine. So the next part of this conversion system is thermoelectric effect with nano elements, because here we got some problematic with situation of this pellets with cold and hot side, and so we know new technology which research now is on the cold pellet. We can put nano elements on surface.
Oh, sure. Maybe we can use it in our parts, all the plants.
Yes, you're right, because we also can use this effect not only on this pipe. We can use it on equipment which can be heated during the manufacturing on other parts and have electricity from it. So another part is filter under our chimney, because when this is filter, they manufacture from one enterprise. They have inside system of reburning of waste, and the generation electricity inside it too.
Also, it has a big CO2 emission, which is stays inside the chimney. So we want to use a spatial concrete which absorb this CO2.
So here we just show that we can supply the plant and we can supply our house holes. So next. Here economic parts, we calculated about this turbine, about consumption of human pressure, and this is enough for 100 household, and it is a global implementation, a profit from it.
And I would like to talk to you about osmosis. Osmosis is a natural phenomenon occurring between two solutions of different concentrations. For example, salt water and pure water separate of membranes. A flow of water is naturally induced from the low to the high concentration solution, and this flow and this which tends to equilibrate the concentration on each side of the
So
membrane.
another additional is water heating system supplying templates and
Thank you very much.
Have you calculated what would be the pressure drop in the chimney?
We calculated pressure. It's on the first.
The one if you put everything inside, I think we may not the chimney itself.
We calculated the pressure first here on this turbine when we do an economic calculation. It's like here it was like 3.9 Pascal, and here we calculated like of U, which goes most like 3 or 6.5 tons which going, and then we calculated that in this case we can use also another cascade of turbines, and that system of thermopairs, which you are asking about, the thermopairs, about filters, about all system under this pressure, they, and also the filters, they are manufactured from special materials and construction to work in extremely hard conditions.
Any other questions? Okay, thank you. Fine. Please come and present your work. Please, you can get ready.
So hello everybody, we're Team Economics Maki from the EBEC study, and we will show us the way we decided to tackle the problem we gave us. So there are at least 3 points we wanted to focus on. First, inefficiency, pollution, and social welfare. And we will talk about social welfare more in detail during the presentation. So let's show what our main idea actually is. So sorry for the interesting picture, you know. So we have a factory that wastes energy. So we have heat that is brought, that is forced to go into a chimney. And what we wanted to do is actually to create a coil. Hot water that comes from the water network of the town itself actually flows into the coil itself, so that water gets hot. So we have hot water that can be sold to the town, and at the same time, the hot water can initialize a whole RC cycle thanks to a liquid which has a boiling point which is lower than the one of water itself. So we can do some electricity production as well, which is really important. And at the same time, what we thought that could be handy, especially because of the low price of this object, this innovation, could be a CO2 filter. This is due to the fact that actually with the CO2 factor, you're able both to reduce your consumption, and especially your production of CO2, and at the same time, you're able to trade the CO2 to other kind of firms who work in several different kind of industries. And let's go to, well, the next slide actually illustrates more the details of the whole CO cycle and at the same time of the CO2 filter we decided to implement. And let's go actually to the pros and cons of this quite simple solution. The main con is the fact that we have no data about financials of the firm, about the size and the dimension of this firm. And at the same time, we have several advantages that will be further explored and discussed in the presentation itself. If we look at the main drawback, the heavy capital injection that is required to actually make this kind of innovation, we can actually notice that although there are a few codes that are nearly scalable with both the production and the CO2 emission, so that we can do a break-even point analysis according to the dimension and the scale of our production. There are several advantages that should be better explored and that allow us to describe the way actually this project could be, for instance, financial. So we have the problem of funding this kind of innovation, and although we have several advantages such as the commodities-related plants, and especially we have hot water that can be sold to the city, and at the same time we had some kind of electricity production so that we can reuse some kind of electricity to lower the demand of the firm for such kind of utilities such as electricity. We have some really interesting CO2 advantages as well. And this becomes really interesting if you consider the cap and trade method that is utilized by the European Union in order to limit the production of CO2. As a matter of fact, we have this kind of carbon credit, which is cap and trade method, according to which, if you want to produce and if you want to produce things that actually bring an emission of CO2, you have to pay for each ton of CO2 you're actually producing. So, if you can actually install a filter that allows to, I don't know, maybe to halve, maybe to reduce the CO2 emission into the atmosphere, what you can do is actually to augment the production so that economies of scale and economies of volume can actually kick in so that we can reduce furthermore the operating costs of the firm itself. By the way, this will also allow us to enhance the way actually consumers, current consumers, perceive our firm itself in terms of brand equity. So if our firm is actually green, if our firm cares for the environment, we have more positive impact on consumers as well. And let's go to the last and probably most interesting point, social benefits. So utility, especially in an economic point of view, can be seen as a negative externality. That is something that doesn't allow the whole economy of the nation to actually allocate goods and services in the most effective way. So what we can actually find when talking about pollution is finding a situation during which you can have actually a Pareto efficient solution. Okay. So let's see what happens. We decided to ignore at first what happens in the market of water and electricity. Those are important. We can assert that actually what happens is the fact that, that can be eliminated from our reasoning. If you want to know something more, you can ask us later on during the presentation. If we talk about the final... Okay. Thank you.
Thank you, guys.
I'm sure that your idea will be cheaper. So energy, what you will get, will be cheaper than exchange.
So the energy we actually let's talk with the point of view of the firm of the manufacturing carbon. So if we consider what actually happens, is the fact that the firm requires electricity to manufacture to create steel, and it's producing electricity at the same time through the OCR. So if we actually consider what's happening, we can see that if the firm decided to sell electricity to the city, the price would be necessarily lower because it would become a competitor of the power plant accessing the city, the nation, the region, etc. So electricity in this case is not just a way to produce and sell electricity, it's a way to increase the efficiency of the firm itself, because you require less electricity and you reduce your operating costs.
Thank you. So next up is Greece, and we're going to finish all the presentations with Nordic team.
Hello everyone, we're the members of the Greek team. I'm Marios, this is Konstantinos, Consiglus and Alexandros, and this is our case study. So as we all know, the problem was how to get waste heat from factories and create a heat recovery technology system in order to gain some benefits, for example, financial and environmental. We designed a solution where flue gases can provide energy for electricity, hot water, house heating, and cooling, and all of them all at once. So, Franciscus will talk more about this.
Okay, so let's start with flue gases converting them to electricity. We're using the typical organic cycling machines that are well studied and implemented right now. They transform hot gases around 200 Celsius degrees, like our gases, to electricity, with an efficiency factor reaching up to 0.8. They're having capital expenses around 7 to 10 million euros, which looks a lot, but the estimated payback time of the implemented systems is around 4 years. Their lifespan is 25 years, and they use materials like carbon steel and aluminum fins, because the steam is actually at a low temperature and might get hot water and corrode the pipes. So our second solution is to transform flue gas actually to convert the energy of flue gas to hot water. We're using a thin coil recovery system, again a classical solution. That was hot water at 75 degrees Celsius that can be used for hot water at the houses. It has a low price per unit, around 5,000 euro, and they can be distributed around 130 houses of a small town case. And the expected payback time is 1 year. It can be connected with the existing hot water grid, or we can have a novel construction of a new water grid and have competitive prices with the existing one, if it was a private investor. And we can, again, it's built from stainless steel, so no corrosion can happen.
So regarding the use of fuel gases for housekeeping, we have searched through the internet and we have found some case studies which are already available and are trying to deal with that problem, and especially for Riga. In our case now, using data, we have tried to make an estimation about the power demand of the area, and it was about 45 megawatts. So in our case, we have to establish our own distribution network. So we are about to have high capital expenses, approximately 5 million, but fortunately there will be almost no operational expenses. So we may assume that this investment is probably appealing for private sponsors, because they're going to have a quicker payback. As we can see here, another interesting thing is that using low temperature hot flue gases, we can have, using an absorption refrigerator, we can have cooling, refrigeration, and ventilation.
Now let's talk about the benefits of our case studies. Regarding the hot water solution, we have integration already installed grid, as we mentioned before, and the gases are already in low temperatures, and we can use them as they are in the temperatures. Regarding the housekeeping, we have reduced heating costs about 240 euros per year, and reduced carbon emission about 1.4 tons per house. Regarding electricity, we have no carbon emission and pollution, and the charging for electric cars is very cheap. regarding the cooling system, we use only 39% of electricity compared to mechanical refrigeration. Regarding the benefits for society, for the environment, we have the social benefits are that we have a reduction of the heating cost because of the recycling of the waste stream. There are new jobs and more independent government. Regarding the factory, we have reduced maintenance expenditures, energy production profit, and social responsibility because of the novelty of the factory. Regarding the environment, we have reduced emissions of carbon and nitrogen and reduce energy costs. Also, the car owners will be benefited because of the reduced cost of the electricity. So that's all. Question?
Have you started getting about the business model? Post technical phase, which is fine. But now you're gonna invest, you're gonna build it, you're gonna run it, you're gonna pay it.
Well, the business model actually has two main issues. The first one is how we're going to sell the electricity or just distribute it in the factory and car chargers. There is a tactic that we use that the electricity can be promoted and advertised by car charger, the electrical car manufacturers, and they can sponsor the whole project of recycling heat from chimneys. And secondly, the distributed heat can attract private investors' interest due to the low short payback times and the low operational costs. So it's mainly private investors. And actually the materials used and the appliances can be sponsored by companies that create it because they're having a monopoly in some cases.
What was the cooling? You have mentioned the cooling process. Why don't you use it?
The cooling process, yeah, it can be used as an alternative for summer. I mean, you can use it in large supermarkets for ventilation or in large gathering areas. And also for refrigeration, if it's needed.
Thank you. And the last one after finish this working day will be Nordic team. Please come.
So, hi everybody. My name is Erica. I'm Johanna.
And I'm Wanda.
And we are the Nordic case study team. And today we're going to talk a bit about the case, show you our analysis, and present our solution, and in the end, summarize it all for you.
Okay, so this case is about a small society with waste disposal, with heat waste problems. But is heat really a problem? Well, considering the climate in here right now, I understand if you think so. But when concealed in a chimney, like in this case, it's really a huge potential. This can be a potential for a lot of different parties. For example, the factory can use it to become self-sufficient, or it can use it to support new production. The households can use it to receive electricity or heat. The community can use it to common facilities or to develop support for new production. Or we can use the received energy to trade globally. Well, a commonly known solution as of today is with district heating. The problem with district heating is that you will be depending on a third party. And especially with a third party with unknown closing time, we will have a dependence that's really a big problem. And to come around this dependence, we have to build a second system, and that's not just financially justifiable. So therefore, we have decided to go further into another option that is not only a great potential, it has the possibility to lower the
unemployment rate, and really justify everything for the society. We have shown some support from you guys.
All right, so in a perfect world, a certain food will only grow where it's naturally environment. But unfortunately, that's not currently the case. So therefore, we would like to use the excessive heat to heat greenhouses. Modern food production needs a lot of energy. And by using heat that would otherwise be wasted, it can be possible to decrease CO2 rates. Also, producing food on a local basis minimizes transports and creates job opportunities. So, there are good technical solutions on the market for this kind of thing. For recovering wasted heat. In this case, a recuperator could be an option. The heat is collected in connection to the chimney and then transported. The greenhouse would be situated close to the chimney to make the process efficient. The amount of wasted heat in the factory would be enough to support a medium-sized greenhouse, big enough to support all the 130 households in the village. Hopefully, the solution is applicable to an already existing greenhouse. In case we would only need to pay for installation and, well, basically just for installation. If we have to build a new greenhouse, we also have to pay for materials and for construction. Maintenance costs will be covered by sales from the greenhouse, so food sales.
We also made a SWOT analysis of our greenhouse solution. So as you can see, some of the strengths are that it's financially justifiable and it's also environmentally friendly. There are many opportunities with this as well. For example, you could decrease food transport, and you can also decrease unemployment. There is also some threats though, and for example, if the factory that is providing the heat to the greenhouse would go bankrupt, we see it as a real possibility. So, to conclude, this is a green and sustainable solution that could decrease unemployment and could possibly be developed and used all over Latvia.
It's again the same. I mean, the solution we have seen similar solutions before, but again, about the flexibility in the summer. How do we deal with that?
Yes, we thought about that, but the possibilities we see here with the increase in the society of decreased unemployment and better economy, we see it as a bigger potential than to use all of the possible energy.
We think this is solvable.
It's a very nice presentation and it provides a good background for the choose for the factory needs or its local chemical needs or those management.
That was the last team presentation. I want to say a big thank you to you all. You did a great job. It was a hard task, especially for the time given. But you are one of the best in the Europe. As you are here, you should be very proud of yourselves. Now, until lunch, relax, have some fun, and have some free time. See you tomorrow. Thank you. And if you have to go to your rooms for some things, I'm sure that's welcome.
students to each other.
Go around.